Now we'll start working on deriving the solution. The easiest part to get is the Q dot. So we'll go for that first. That's the volumetric flow rate. Q dot depends on the normal velocity going into the area of the blades, obviously. If that's the only velocity that's on our idealized model, there's only a normal velocity to that surface. So that fluid velocity times the area of that inlet surface is going to give us a volumetric flow rate. So we have an area of the inlet surface and we multiply that by the normal velocity, and that will give us the total volumetric flow rate. So that seems pretty straightforward. The area coming in, well, we've got a circular situation. The fluid is coming in all around the circle from the center into this blade region. So the fluid's going this way. This is our Vn in, all entering that blade region. Question is, what is the area of that surface? Well, of course, the radius here is R1. We know that. So it's going to be 2 pi R1 and then times the thickness of that region. So in and out of the page, there's a thickness that we drew last time. And so that's going to be our total surface area of the that's being crossed by the fluid as it enters the blade region, the impeller region. So we can easily calculate that. That's 2 pi. We know R1 is 0.09 meters, and we know that the thickness is 0.05 meters. So that gives us an area of the inlet surface of 0.0283 meters squared. So no problems there. We know how to find Vn in because that's the last thing we found in the lecture prior to this. So Vn in, we said that was equal to U1 times the tangent of beta 1. And we've been given beta 1. Beta 1 was 30 degrees. So we know that, but we need to find this U1. Well, U1 is the blade tip speed of the blade at the inner surface. So that's going to be this speed right there. The speed at which this blade is moving. Movement is going to depend on that rotational angular velocity of that axle. So we know that U1 by simple geometry is going to be the angular velocity in radians per second times the radius. And we know the radius, but we do need this angular velocity. The angular velocity is given to us in RPM, 1400 RPM, which of course is equal to 1400 in radians. It's 2 pi radians per round. So I put radians there. And then I have and this RPM is per minute. So I'd have that. So it would be 2 pi times 1400 radians per minute, but I don't want radians per minute. I want radians per second. So it's going to be 2 pi radians divided by 60 seconds, which is the number of minutes number of seconds in a minute. So these minutes will cancel, radians will do that. So they'll do their thing. And we get that the omega is 147 radians per second. 147 radians per second gives me that 1400 RPM. I can then calculate U1 based on that. So I have 147 radians per second times my 0.09 meters. So that's my R1 coming from this equation here. And so that gives me 13.2 meters per second. So my U1 is equal to 13.2 meters per second. Great. So I can use that now to calculate my Vn in. So what I want is Vn in, because I need Vn in to get Q dot. So I've got my U1, I've got my beta, I can just plug all that in. Switch page here. There we go. So my Vn in, my normal velocity going into my pump region is the 13.2 meters per second for U1 times the tangent of 30 degrees. And I plug that into my calculator, and I get that the normal velocity at the inlet to my pump region, 7.62 meters per second. All right, so there's a good result. I've got an inlet flow velocity into my region, into my pump region, my blade region. Now I can get my Q dot. My Q dot, I said, was 7.62. That's Vn in times that's meters per second times the area I found for that inlet surface, 0.283 meters squared. So my Q dot comes out as meters cubed per second, which makes me happy because that is a volumetric flow rate. And I get this. I get that my volumetric flow rate, my first result that I've been asked to find, is 0.216 meters cubed per second. Okay, that seems pretty good. As I said, our inlet idealization is that VT in equals 0. So our idealization is that VT in equals 0. That means there's no tangential velocity of the fluid as it enters the blade region. It's coming in only normal to that surface. So if we want to find the water horsepower, we can use our equation rho Q dot U2 VT in, VT out minus U1 VT in, but we just said VT in was equal to 0. So that's going to kill that term because VT in is 0 by our assumption, our idealization. So my water horsepower equation is rho Q dot U2 VT out. So that's pretty simple seeming, except that I don't know VT out here. So U2 I can find. U2 is going to be the blade tip speed at the outer edge of my blade region. So I've got that okay. That's going to be the speed right here, U2, and that's going to be based on R2 and just the omega, which I now have. So using omega and R2, I can find U2 here. So that's not a problem. But VT out, that's the tangential velocity of the fluid as it leaves through this outer surface. And we don't know what that is. So that's what we're going to have to go after in the next little lecture bit.